Hi everyone, it's nice to meet you. And today I'm going to talk about how we can reconstruct the position of 3D objects with 2D videos using non-expert crowds of annotators and a new particle filtering based aggregation strategy to integrate information that cannot be found in the pixels of the video alone. So our eventual goal with this line of work is to enable autonomous vehicles to be trained with simulated data so that we can create safe systems much faster compared to current approaches we'll be able to. For autonomous vehicles, the acquisition of training data set is crucial. However, for important but rare events such as car crashes, it's very hard to collect these 3D dataset in the wild. For example, Google had a fleet of 55 autonomous vehicles test drove for about 7 years, and they drove in total of 1.3 million miles. However, in the US alone, the statistics says that a single crash happens every 62 million miles. And this means that it will take about 300 years for this fleet to encounter a single accident data point. And this is too far compared to us wanting safe autonomous vehicles running right now. And let's take a different view. If we go to any online video sharing platforms, there are thousands of examples of existing traffic accident scenes that are took by everyday videos and uploaded by people. And what if we can create realistic simulated 3D scenes from these abundant existing videos that could be crawled from the web? However, the task of reconstructing 3D scenes from 2D video is not a trivial task, and it's actually a strong challenge. And here's why. So first, there are information that cannot be found within the pixels of the videos alone. For example, the size of the objects, or the speed of the objects, or the camera parameters like focal length. These aren't in the raw video data. And also, we don't know what pixels correlates with the objects and what correlates with the background. And it gets even harder if the objects that we are interested in are occluded or truncated. But there are actually resources that these information is available. There are some information that are available in the web, some are available by human perception, and some are available by the computation using computer vision. So now the problem is that if we can use these available information, how are we going to tie these and bind these information into the video pixels? So to tie these information and bind them to the pixels, we propose human-machine hybrid systems that can do this. The system we introduce has the video as an input and estimates the position and orientation of the target object so that we can reconstruct the 3D scenes. And we use crowdsourcing to do this because it's flexible and scalable, and it's a quick access to human computation. And for the annotations, we used dimension line annotations, which are basically the length with height lines of the target object. And we use this because it's very easy to use for even non-experts, and we could even convey the depth information if needed. So with the system, is the problem solved? Are we just good to go? Unfortunately, there is still a severe challenge remaining, and it's about the accuracy of the final reconstructed 3D scenes. So even a small error in the 2D annotation can get significantly amplified when we reproject it into the 3D domain. If you see the example in the image, this is an example from an actual crowd worker who participated in our experiment, and the error is only 3 pixels different from the ground truth. However, if we reproject this into the 3D space, it can become up to 26-meter difference, which is a huge error. So in this task, the quality control becomes a crucial step both in the annotation aggregation stage and also in the 3D state estimation stage. So to resolve this, we propose this core idea of leveraging content diversity, where it means combining annotations from workers viewing different instances, in this case, different video frames of the target object. Let's say we want to annotate the dimension lines on the N frame. So N frame is our current targeted frame. But as you can see at the white fan, it's really hard to see the length dimension because it's hidden because of the view angle. But if you look at the previous or next frame, the length dimension is visible. So our idea was, what if we can integrate and borrow the annotations from these neighboring frames? And we used particle filtering based aggregation method to do this. And another benefit of doing this was that we can now do more aggressive filtering to filter out the poor annotations as much as possible before the post-processing steps. And we could even have like missing annotations for a certain frame because we could borrow from the neighboring frames. Here's a brief introduction of what particle filtering is. It's basically a recursive Bayesian method which iteratively updates the probability density function, which is a represent of the potential hypothesis. And in this case, in our setting, the hypothesis is the 3D state of the object, which is the 3D orientation and position of the object. And we used 3 distributions, and one of the distribution was the measurement distribution, which is computed by comparing the hypothesis 3D state and the actual dimension line, and computing the error. It updated the next hypothesis. And another interesting thing that we applied in our experiment was self-filtering. So we, in our experiment, we encourage workers to self-filter the annotation whenever they feel not confident enough to draw the dimension line accurately. So for the white fan example, where the length was almost impossible to draw, the workers could simply click "I cannot draw" button and just skip drawing dimension line for that entity. And this was particularly useful in our case because for the vehicles, there were cases where it's blur, it's too small, or the view angle wasn't right. So yeah, there were many workers who used this functionality. And as the aggressive filtering, we applied 2 more filtering methods. And one was filtering the whole annotation set from workers, and the other was filtering individual annotations from a set of annotations if it's considered as low quality. And here's the worker interface. If you look at the right GIF image, you can see that workers can draw dimension lines, adjust it, or like add more dimensions line, or delete dimension lines if needed. Okay, so to see if our applied ideas actually helped improve the system quality, we ran an experiment. So we used 17 videos from the Kitty dataset, which is a full sensor-mounted 3D dataset of traffic scenes. And we had total 5 workers annotate each single frames, and there were total 10 frames for each video. And we used Amazon Mechanical Turk for our crowdsourcing platform, and each worker was paid about $9 per hour for their wage. And let's first look at the filtering results. So for the 3 steps of aggressive filtering, we could filter out from 7% to 13% for each steps to get rid of the poor annotations. And what is interesting is the self-filtering result. It's the image on the right side. So for the white van image, we actually use this in our experiment. 4 out of 5 workers self-filter the length annotation. And for the second image, there is a trim where you can't see either the front or back of the trim. 4 out of 5 workers self-filter the width entry because it wasn't visible. And for the last image, all 5 workers self-filter the length entry because the image was too small and the length dimension was not in the right angle. And we also looked at the effect of the filtering. Like we looked at, did the filtering actually improve the annotation quality of the remaining annotations? And the answer is yes. We could reduce the error by 20% significantly by filtering the annotations. And we also looked at the positive effect of the self-filtering in terms of the total task time. So the left sidebar is the hard entries, which means that at least one crowd worker self-filtered because the one thought it's hard to draw. And the right sidebar is where every worker is annotated. And you can see that for the hard entries, for those who draw the dimension lines, they took significantly more time in completing the task. So this shows the potential benefit of using self-filtering to reduce the total aggregated task time, which is related to the cost. And last but not least, we also evaluated the final performance, which is the state estimation performance of the system. So the last item is our proposed method, which is using the particle filtering to leverage the content diversity, which means using particle filtering to aggregate the annotations across different frames. And we tested 3 different window size, but here I will only talk about the window size 3 because that was where we had the most gain. And we compared that with the baseline, where the baseline doesn't use particle filtering, but still use the state-of-the-art optimization method to estimate the 3D states. But this one couldn't leverage the content diversity, the baseline, so it couldn't handle missing annotations. And we also compare that with the particle filtering, but without leveraging content diversity. And here's the result. So comparing our proposed method using particle filtering with 3 windows, we could significantly reduce the position estimation error compared to the baselines. We reduced it by 28%, so there was a system gain by using our ideas. And we could say that the benefit, the gain, was truly from the core idea of leveraging the content diversity, but not the estimation algorithm itself, method itself, because if we compare the baseline with the particle filtering, but not leveraging the content diversity, not borrowing annotation from neighboring frames, there were no significant difference between the performance. Okay, so as a summary, in this work, we introduced content diversity as a means to aggregate multiple annotations from different sources where the content has dependencies between the contents. In here, our experiment, the temporal dependency was the dependency between the video frames. And we also introduced a novel annotation aggregation method that used particle filtering. And the system itself, which is a hybrid intelligence system to estimate the 3D state of objects in 2D videos, was also a contribution. And as a future work, we are working on improving the system in terms of interface and the backend. So our goal is to achieve near centimeter level of error in terms of the final reconstructed scene. And thank you for listening. And any questions?
Questions?
Hi, thanks for your talk. I was wondering if you had thought about adding maybe edge detection overlays to the images to help the users identify those landmarks better.
Yeah, I think that could be an interesting additional functionality to add. But one thing I'm concerned is that whenever I try to do edge detections, it's many times too noisy and depends too much on the video quality, the frame quality. So I don't think there will be a one-size-fits-all edge detection method that will always benefit them. And I hope that wouldn't like distract the workers. But yeah, that could be a good thing to try.
Okay, if there's no more questions, I have one. You noted about your aim to get a centimeter accuracy. And I'm wondering whether reconstructing such a 3D scenario, centimeter is important. Is it a too ambitious goal? Maybe it's not needed. Have you thought about that?
Yeah, I think that's a great question. I think that's a very ambitious goal. So yeah, this is a goal, aim high. But I think we can achieve at least some meter accuracy. And from there, it will be like optimal if we can achieve near centimeter accuracy. So that's our goal. But I can't say like we can do it. We'll have to hard work on that.
Hi, thank you for your talk. This is probably a naive question. So there are software that have mathematical equations embedded, and you can actually reconstruct accidents and so on. So how this is related or different, or what's the benefit of this over the other? I'm not in that area. I just know because my husband works on that. So, yeah.
So thank you. Was your question, what's the difference between a simulation not from real data?
No, from real data. They are adding real data of accidents like speed. They can even take aerial photos of the street and everything. And they try to see whether, by altering parameters, how the accident was actually happened. And this is done mainly for insurance companies or for the court and everything. So I just want to see the relevance.
I think that's a great question. So we have the same goal to have a simulation of an actual accident so that we can play with the parameters to see how we could have avoided the accident. But here, let me go to the first slide if I can quickly. The problem with trying to acquire the full sensor amount in 3D data in the wild is that we don't often encounter these crashes, right? So Google ran 7 years of this in the wild data collection, and they could only encounter 11 light crashes. And this is too little for even a single crash type, but we want to have thousands of these data for each crash type, for example. So I think it's for now unrealistic to only rely on those captured in the wild, and that's why we want to create that with the 2D data set, which is more abundant.
I guess if there are no more questions, it's time to thank the speaker again.